Okay, I'm John Spavacek from Aspen Research. Thanks for coming out this afternoon to listen to my talk. I'm going to talk to you about a project that we did for a client quite a few years ago that came to us. They had a interesting problem, and we ran into a number of unique challenges trying to solve the problem. But in the end, we were able to succeed, and we came up with some interesting results along the way, which is what I want to pass on to you. Let me give you a little bit of background of the problem. This started out in the chemistry branch of the company. The client had developed a UV-cured floor coating. It was based on Thio-lene chemistry. It was two parts, solvent-free, like you would expect for a UV-type coating system, low viscosity, easily mixed by hand, and then it was just applied to the floor with a standard paint roll, leaving about a 3 mil thick coating on the floor. After that, it was cured with UV light. The properties that they had developed in their coating so far were acceptable. They had 4H pencil hardness and great adhesion to the floor, no yellowing. There were other properties, of course, as well, but these were the major ones that they were most concerned about. Now, this was the part that was developed by the chemistry department of the company. The engineering department of the company also had their hand, and they had developed a UV curing system with it. What this was a cart that had 3 different UV bulbs attached to it, transformers and power supply. And it gave a cure zone that was about 70 centimeters wide, 18 centimeters deep. That's about nearly 30 inches wide and say about 7 to 8 inches deep. So when you put the two parts together, the chemistry and the cart, they found that the fastest they could cure the material at was a speed of 9 centimeters a second, which kind of sounds slow, but if you think about it, it's a 2-second exposure time. That's a pretty fast cure. There are lots of materials that need far more UV time exposure than that to cure. But at the same time, too, 9 centimeters a second gets to be painfully slow. It's not so much a problem. The customers weren't that concerned with the fact that a large room like this would take a while to cure, but the fact that the operator was going to have to try and maintain a speed of not more than 9 centimeters a second. That's about the speed that somebody's going to be executed and walks to the death chamber at. So their question to us was, could we accelerate the cure rate by a factor of 10, get it up to about 2 miles an hour, which they thought would be acceptable. I mentioned this is a Thio-lene based system, and you're probably not familiar with Thio-lene chemistry, so I'm going to give a little bit of background with regards to that. Turns out it's a very rich, very well-studied chemistry set. There's been a number of papers that have been published over the last 100 years involving it, several review papers, a couple that are listed there. The first one is actually in open access. You can go to the publisher's website and pull it down for free. It's widely available. But for some reason that I don't understand, the chemistry is not very well used in industry. So that's probably what was mentioned. I'm going to give you the background. Some of the advantages the system has is that you get shockingly fast cures. We're talking about something that cures in 2 seconds, and they want us to try and up the speed to 0.2 of a second. The other thing that's a big advantage with this particular system is that there's no oxygen inhibition. That's something that's always a concern with acrylates, is that if oxygen will get into the top layer of the acrylate coating, and it just stops the reaction. So you're left with a soft layer on top, even if the stuff underneath is cured by the UV. That doesn't happen with Thio-lene chemistry. And then, of course, since it's UV cured, it's solvent-free and all the other good stuff that you come to expect with that. Thio-lene chemistry, you've got two parts. You've got a thiol part and you've got an ene part. Thiol, just through a generic example. Up there, enes, that's where you really get the richness of the chemistry. You can get acrylates, you can get acetates, you can get vinyl ethers. The number of possibilities there is pretty much endless. There's a wide range of possibilities that you can play with. Fortunately, you can use both types of photoinitiators, the Norrish type 1 and the Norrish type 2. The type 1 shown up above there is the type that breaks up into 2 different radicals. The type 2 is the part that stays together and forms just one radical. So I always think Norrish got the terminology wrong with it, but he won a Nobel Prize and I didn't, so I'm not going to criticize it. Chemistry proceeds along a propagation steps shown here. Thiol radical adds to the double bond, transfers the radical to a carbon-based center, as you see in the first part up here. Second propagation step, then the carbon-based carbon center radical, then reacts with another thiol, extracts the hydrogen, leaving you a new thiol radical, and the reaction continues. Another way to look at it is in a circular diagram, which was provided by this source. The one thing about this review paper that I thought was kind of interesting is that this is the only known example of preparing an AB copolymer by free radical polymerization. Normally, if you're doing an AB copolymer, like say a nylon 6,6 or 610 or something like that, it's a condensation reaction. This is the only known example where it happens with free radicals. Interesting. I'm not sure what to make of it, but that's out there. So, termination is the result of just free radical combinations, whether it's the thiol or the carbon-centered radicals, or you could even have combinations between cross-combinations between these two. And then, as I mentioned too, there's no oxygen inhibition in Thio-lene chemistry. What you see here as you go along is, again, carbon-based centered radical. It picks up the oxygen molecule and forms a peroxyl radical. Now, this is at the point where acrylate chemistry has to stop, because this peroxyl radical will not react with the double bonds in acrylates, and that's why they have that oxygen inhibition. On the other hand, the hydrogen here now on the thiol is labile enough that it's able to be extracted by the peroxyl radical, forming another thiol radical, which then allows the reaction to proceed with the propagation steps that we already saw. So if you don't have the thiol in there, you get the oxygen inhibition. By adding the thiol, you're able to get around the oxygen inhibition and allow things to proceed. So now we'll talk about our efforts that we took to try and accelerate the cure. We basically saw that there were 3 independent steps that we could try and undertake to increase the speed of the cure. First was to try and play around with the UV lamps, see if there was some way we could get more effectiveness out of them. Second was to use thermal initiators. The lamps put out a lot of heat, and we were thinking if we could possibly take advantage of the heat that was in there, possibly with thermal initiators get it to cure faster. The last one then was to reformulate entirely with alternate monomers. The table below here shows our perspective as to how much effort we thought and how much risk there was of upsetting the apple cart and losing all the other properties while we were gaining the increased speed in terms of the cure. The lamps would obviously be the easiest, lowest risk thing to do. You're not doing anything to the actual chemistry, you're just doing anything external to it. That'd be the ideal way to go if we get there with just that. Thermal initiators would be a little bit of reformulation work, basically just adding the thermal initiator to the system and hoping that nothing else goes wrong with it. The last one, of course, then would be just you're taking everything out and starting all over, putting it back together and hoping you can rebuild what you had before. So with the lamp optimization, the client had told us there were a couple options that we could not pursue. The first is they wanted to be able to install this floor coating in as many places as possible without regards to worrying about what utilities are available. So they limited the power draw of the cart to 15 amps and 120 volts AC. Basically, pretty much any house or office or commercial building in the country should be able to supply the electricity that the cart needs. And the cart was already maxed out with regards to that. 3 bulbs that were there were drawing more or less the 15 amps, and so we couldn't add more bulbs or more higher wattage bulbs. The other thing they told us that we couldn't do was decrease the distance of the lamps to the floor. They had tried doing that early on in the design and ended up melting some vinyl tiling in the process, and so they ended up backing off to what they thought was a safe distance, and they said we can't go any closer. What they did leave open, though, as an option was to install newer bulbs and better reflectors. The bulbs, as I had mentioned, were supplied by the engineering department. They'd been something that had just been floating around there. Nobody knew how old they were, how long they had been used, what condition they were in. And same with the reflectors. They were homemade as well, and so that was viable as an option to us. So we got new bulbs, put those in, ran the intensity spectra of the two. In the areas of interest in UV, down here below about 400 or so, you can see that the new bulbs with the red line here were about 3 times brighter than what the old bulbs were. And we saw a similar type situation when you look at the reflectors that were available. The upper picture here shows what the reflectors were like. There was some shiny metal here, but there was surrounded by tremendous areas of rusty panels that were doing absolutely no good at all in terms of reflecting the bulbs or reflecting the light.